Hi guys, so in the previous two videos, we have discussed first the double structure of a random variable, and then we moved on to proving that the mean of the distribution of x, that is the random variable x, is equal to the mean of the distribution of x bar, that is our estimator. So in this video, that is the third part, we're going to prove that the variance of the distribution of x bar is smaller than the variance of the distribution of x, that is the random variable. So we've already seen, by the way, I'm not going to repeat that. If you have not already watched the previous video, you can do so now. So I've already shown diagrammatically that if, for instance, this is the distribution of x and this on the right hand side is the distribution of x bar, so we can see at a glance that even though the mean for both of these distributions, when we compare them, the mean is the same, but the variance is not the same. So in this video, we're going to prove this. Okay, so let's start. First of all, let me just clear up the space. Okay, so first of all, like we did in the previous video, we're going to start by plugging in for x. So the variance of x bar is equal to 1 over n times x1 plus x2 plus all the way to xn. So here all that we have done is plug in for x bar. Okay, so far so good. Next, we can use variance rule number 2 to bring out 1 over n as a common factor. So let's do that. And as always, we should explain why we're doing what we're doing. So this one is variance rule 2. Okay, cool. So what we get is 1 over n squared times the variance of x1 plus x2 all the way up to xn. Okay, cool. Now, this is the stage which requires a little bit of thought once again. Like in the previous video, we imagined the difference between the planning stage and which is basically the beforehand stage. So we argued that the expected value of x1 is equal to the expected value of x2 is equal to the expected value of xn, and all of these are basically equal to mu x, right? This is what we did in the previous video. Similarly, what we're going to do now is that we're going to think about the variance of x1, and let's just focus on x1 for now. So we're going to think about the variance of x1 as a beforehand concept at the planning stage. Okay, so when we're still at the planning stage, this is the stage where we do not yet know what the value of x1 is going to be, right? At the planning stage, we don't yet know. All we do know is that it will be generated randomly from the distribution of x. So the variance of x1 as a beforehand concept is therefore going to be sigma squared x, right? So similarly, the same is going to be true for all of the other sample components, thinking about these as beforehand concepts. So we're basically applying the same reasoning for the variance as we did for the mean, okay? Mean of the distribution. So, and the variance of the distribution, okay? So over here, I'm going to note down the reason as a beforehand concept. Variance of x1 as a beforehand concept is same, sorry, is sigma squared x. The same is true for all other sample components. Okay, so using this reasoning, we can now move on. So over here, this becomes 1 over n squared times the variance of x1 plus the variance of x2 plus the variance. Okay, so let me just put a dot dot dot. Yeah. Now, in principle, obviously, we have a lot of, this is xn. Let me just finish this. So in principle, obviously, we do have a lot of covariance terms. So we also have to note the fact that the covariance terms are just going to equal 0. So we have to note the fact that assuming that the sample values have been generated independently, so we should always explain every step in order to get full marks, assuming that sample values are generated independently. All covariance terms equal 0. Okay. Therefore, what we get is as follows. So this expression right here now becomes 1 over n squared is equal to sigma squared x plus sigma squared x plus all the way to xn sigma squared x. So this is what we're left with. Okay. By mistake, I inserted this equal to sign over here. I'm sorry about that. Okay. So this is now equal to n times sigma squared x over n squared. Okay, because we have sigma squared x, we have this same term n number of times. So therefore, we can just write n times sigma squared x, and the n will cancel out in the numerator, and this will just leave us with sigma squared x over n, and that is our answer. Now, basically what we were trying to show is that the variance of the sample mean, sorry, the variance of the distribution of x bar is smaller than the variance of the distribution of x, right? So let me just continue on the next slide. Okay, so this is what we got as our answer. So the variance of the distribution of x bar equals the variance of the distribution of x over n. So this is what we got, right? Now notice that this number over here, whatever it's going to be, is going to be smaller, right? So therefore, we have proven that the variance of the distribution of x bar is smaller than the variance of the distribution, because we're dividing it by n. So obviously, this is going to be smaller than sigma squared x. So smaller than sigma squared x. So we were comparing the variance of the distribution of x. Let me just redraw the diagram once again. So I don't know why I can never draw the curve correctly the first time. Okay, let me just draw it once again. So yeah, I think this is much better. Cool. Okay. So this is the distribution of x bar on the right hand side, and this is the distribution of x, the random variable, on the left hand side. So we proved in the previous video in part 2 that the mean of the distribution of x is equal to the mean of the distribution of x bar, and in this final part, that is part 3, we have shown that the variance of the distribution of x is larger, or in other words, the variance of the distribution of x bar is smaller as compared to the distribution of x.